Hello and welcome to part 3 of Unit 8. In part 3, we're going to develop the concept of potential energy. To begin with, we're just going to look at energy in general. So there are many types of energy. We have nuclear energy, which is fission and fusion. We have chemical energy. Food, eating is converting chemical energy into other types of energy. Striking a match. We have electrical energy. We have electromagnetic energy with radio waves and light, and thermal energy with the internal kinetic energy of things changing. So when you add energy to soup, the molecules move around a lot faster, and that raises the temperature. And then I skipped this one. Mechanical energy. Okay. Mechanical energy is really what we are focused on in this unit. So mechanical energy has two parts to it. It has kinetic, which we've already encountered, and potential energies, which we're going to give the letter U in this unit. Okay. So this top part is very much devoted to developing the thought of what is a potential energy. Okay, well, what is a potential energy? In reality, it's just work by another name. Anytime we have a work due to a conservative force, we do this over and over and over and over, and therefore we kind of skip the integral because it always gives the same thing and just define this thing known as a potential energy. Okay, you will encounter 3 throughout Physics 221 and 222. You will encounter gravitational potential energy, GPE, elastic potential energy, EPE, and then in 222 you hit electric potential energy, but we're not going there this unit, other than that little bit. So, potential energy. Okay. By definition, the change in a potential energy to go from point A to point B is the negative of the work to go from A to B. Bringing in the definition of work, which we know a little chunk of work is a F dot dr. We can now say that a little chunk of potential energy will be a negative F dot dl. And you're like, dl? Where'd the L come from? Well, it's a little chunk of length. dl is a little chunk of length. Okay, which if you think about it, a little chunk of displacement, that also is a little chunk of length as well. But the dl is kind of acknowledging the fact that this can change the direction depending on what the force is doing, like with friction. If we think about our force being written as an x component plus a y component, we can now define these x and y components in terms of the potential energy, assuming that force is conservative. So the x component would be the partial derivative of the potential energy in the x direction, and the y component would be the partial derivative of the potential energy in the y direction. I think I said that all correct. Okay, let's calculate the potential energies for the 2 forces that we're going to be working with that are conservative in this unit. One is the force due to gravity, which is given by negative mg in the j hat direction. So the work to get from A to B will be the integral of this force, I forgot an arrow, dotted with dr as we move from point A to B, which simplifies down to, notice I'm changing my limits, I will explain in a minute, negative mg dy. And since our integral is over only in dy. That means our lower integral is whatever the height is in the y direction, and or whatever the height is at point A, and the upper limit is whatever the y vertical position is at point B. And I should say for this, we are assuming that up is positive and the y direction. Right? Assumed coordinate system here. This integral, we've done it once before, is going to be negative mg times y evaluated from the position at A to the position at B, which is negative mg yb minus ya, or more simply, negative mg times delta y. The potential energy, or the change in gravitational potential energy to go from point A to B, will be the negative of the work to go from A to B, which will just equal mg delta y. For elastic potential energy, we need to bring in the force due to a spring. That is given by Hooke's law. There's a negative sign. K is the spring constant times distance. So this is telling me that the more I pull the spring out, the more the force tries to pull it back in. And I'm assuming that our spring is being pulled out horizontally. We could do the same thing vertically. It would be negative ky in the j hat direction. Okay. If we now think about the work to go from A to B, this would be the integral of f dot dr from A to B, which will be negative kx dx evaluated from xa to xb, for changing the limits similarly to how we change them for finding gravitational potential energy. Doing this integral, I end up with negative kx squared over 2 evaluated at xa and xb, which is negative k over 2 xb squared minus xa squared. So the elastic potential energy will be the negative of the work in this case, which will be k over 2 xb squared minus xa squared. Often you will see this simplified down to just 1/2 kx squared, and there is an assumption with this form that this x is measured relative to the equilibrium position. This concludes this part of Unit 8.